Hello, this is Module 10 of Introduction to Engineering Vibrations. Today's learning outcomes are to review static equilibrium. This will be a review from your statics course, if you took it somewhere, or my earlier courses, Introduction to Engineering Mechanics and Applications of Engineering Mechanics. So if you need that as a review, you could go back and look at those courses. Then we're going to solve for the static equilibrium of a simple single degree of freedom system. So this is where we left off last time. We had three actual real-world systems that we modeled with springs, masses, and dampers. I'm going to look at the one specifically in the mode of the bungee jumper. And for now, I'm going to take away the damping. We're just going to have a springing action. And I want to just look at the damper or the bungee jumper when they're moving up and down without slack in the bungee cord. And so it'll be more like this system, which also has the same type action, up and down with a spring at the top, no damper, and a mass. This is obviously an actual real-world system, but it could also be a kind of a prototype or a model of perhaps some sort of a amusement park ride where you get into some cabinet or compartment maybe, and they let you go and you bounce up and down and experience the amusement park ride. So let's look at this system in detail. First of all, I want to do in this class this video a static equilibrium analysis before motion takes place. And so to start with, all I have is my spring, and there's my spring, and it's hanging down at some unstretched length. We're going to say that the spring is massless as compared to the mass, and so there's no force in the spring. It's just sitting there. And then I'm going to add on the mass, and when I add on the mass, the spring is going to, here it is unstretched, and then it's going to go ahead and stretch down until it's in static equilibrium, not moving, not vibrating, just hanging there. And so it's stretched some distance, which I'm going to call delta, and now there's a force in the spring that balances the weight of the mass. And so the force in the spring comes from that delta. Now the delta I've drawn on my slide here is much smaller than the one we saw with the actual mass, but it can be any distance that it needs to be, whatever it actually is modeling. So the delta, the stretch in the spring, is the length after the mass is attached minus the unstretched length when there's no force inside the spring. And so I'm going to draw a free body diagram. You should be used to this from your days looking at static equilibrium. I have that spring forced up, which is KL minus L0, or K delta, and we have in static equilibrium the weight of the mass down, mg. And that's going to be equal to 0 because we're in static equilibrium. I'll go ahead and sum forces in the y direction. I'll take up as positive for my sign convention in assembling the equation. So I've got K delta minus mg equals 0. And so K delta equals mg is the static equilibrium spring force, and it's balanced by the weight throughout motion. So what I mean by that is, even after we go into motion, here the spring force in static equilibrium is K delta and balances the weight mg, but even as it moves, K delta is always going to balance that weight force. And so we'll be using that as we move forward in the future modules. So that's the static equilibrium analysis. We've completed that. We've solved for the static equilibrium of the simple single degree of freedom system, and we'll move on from that when we get to the next module.